guys, and welcome back to the PyTorch tutorial series. Today we're going to start a new concept known as gradients. Gradients are one of the most difficult concepts to master when learning about PyTorch. So I'm going to dedicate one whole video for understanding the theory behind gradients, and I'm going to make another video to explain how to implement gradients using PyTorch. So before we get to gradients, let's first explain why do we need a computation graph. A computational graph is a type of directed graph where nodes describe operations and edges represent the data or tensor flowing between these operations. As you can see from the image, this is a simple computational graph, and the nodes x1 and x2 represent the inputs to the function y, and w1 and w2 are the edges. These might be additional parameters or weights that are passed along to the function y. In PyTorch, the computation graph is built up as you define your model. So there are two types of computation graphs. The first one is a static computation graph. In TensorFlow, the graph that we use is static. As its name suggests, it means that we create and connect all the variables at the beginning and initialize them into a static, unchanging session. They are computationally faster, but they're not very flexible when it comes to debugging. Some people might be familiar with computational graphs when working with TensorFlow. But the one that we are using in PyTorch is what is known as a dynamic computation graph. Since the graph is generated on the fly, it is called dynamic. This allows us to change the architecture during runtime. They are relatively slower when compared to the computational graphs used by TensorFlow. But while debugging, it is easier to locate the source of the error, and they're much easier to manipulate and change. Before we delve into computational graphs, let's try to define some common terminologies used associated with a computation graph. As we can see from the figure, the computation graph has three kinds of nodes. The blue ones indicate input nodes, the orange ones indicate parameter nodes, and the yellow rectangles indicate computation nodes. The first ones, painted in blue, is a tensor matrix vector or scalar used as input to the computational graph. The second one, parameter nodes, which are painted in orange, are nodes where the parameters of the model are stored. These can be the weights or biases. Our goal is to calculate gradients for these parameters. Next is computation nodes. These are painted in yellow and are used for computation of the output. We also have intermediate compute nodes where we compute the previous node's inputs or parameters. So this might be the final computational node, but as we go further, we might have intermediate computation nodes in between. So this is the example just represents a simple computation graph for a linear regression algorithm. Other reminders: a leaf node means that no operation tracked by the gradient engine created it. Generally, in neural networks, they are the weights or inputs. There might be some nodes in which the operation is not being tracked by the gradient engine. If that's the case, it is known as a leaf node. Next is an edge, represents a function argument and also data dependency. So an edge might be any argument that might be passed to the computation node. A node with an incoming edge is a function of that edge's tail node. So this is basically saying that if you have a function of another function, then this is the edge. So this function is basically a function of another function. So a node with an incoming edge, since the next function has an incoming edge, it is a function of that edge's tail node, which means the tail of the edge is another function. A node knows how to compute its value and the value of its derivative with respect to each argument edge times a derivative of an arbitrary input. First, let's see about forward propagation. And we're going to use a simple computation in order to demonstrate the forward propagation algorithm. Here we have the function z that takes x and y as inputs, and eventually it will produce the cost j. So we have a computation known as z, which multiplies x and y and gives us the final cost j. So let's say that x and y are 2 and 4 respectively in this case. First we can apply a forward pass and calculate the output z equal to x times y, which is 8. And this is given z is equal to x times y, and z is equal to 2 times 4 is equal to 8. So next is backward propagation. Our goal is to calculate the gradient of the cost. Most of the time when using linear regression or other types of algorithms, we must calculate the cost and then we backtrack and try to compute the gradients in backward propagation. To do that, we need to calculate the partial derivative of j with respect to x, and also calculate the partial derivative of j with respect to y, which is dj with respect to dy. So this is the partial derivative of z with respect to x, and we can substitute z by xy. And when we take the partial derivative of xy with respect to x, it's just y, because y is considered to be a constant and x is the variable in which we are taking the derivative. Here we can also calculate the partial derivative with respect to y, and in this case we have x, since we are taking the derivative with respect to y, and x is considered here as a constant. In order to understand the backpropagation path, we need to understand one simple rule called the chain rule. So in calculus class, some of you might have learned about the chain rule, and it is used when we have two functions g and f, where f depends on the result of a function g, and function g depends on some value x. So let's say the first computation g takes x as an input, and the second function f takes g as an input. So the final output will be f of g of x. Then the derivative of the function f with respect to the parameter x, so the final function f with respect to the original input x, is equal to the product of the derivative of f with respect to g. First we must compute df with dg, and then multiply it with the derivative of function g with respect to x, which is dg with dx. Then when we take the product, you can see that we can cancel dg by dg, and the remaining one will just be df with dx. Now that we have covered the chain rule, next we need to go back and apply the chain rule method to find the back propagation for this computational graph. So first we need to compute the local gradients dz with dx and dz with dy, and we have already done so by using dxy with dx equal to y and dxy with dy is equal to x. And in order to compute dj with respect to the original x, it must be dj with dz, which is another local gradient, multiplied by dz with dx. This gives us dj with dx. If we take dj with dz as equal to 5 and dz with dx equal to y is given as 4, then the product might be 20. And when you take this path from dj to dy, then you must multiply dj with dz with dz with dy. Then the value is 5 for this part, and x might be given as 2. Then 5 times 2 is equal to 10. Notice that we are using the chain rule in order to compute the dj with respect to x and with respect to y. And since we have a function of another function, since dj is a function of z and z is a function of x and y. So according to the chain rule, dj with dx is equal to the product of dj with dz and the local gradient dz with dx for the case of x. Next we have some reminders. Here we constructed a very simple example so that you can better understand the idea behind the chain rule. Notice that in this case both the input and the output values are scalars. So far we have only considered scalars as the input. X is an element of real number, y is an element of a real number, which means it's a scalar, and the derivatives that we are computing are also real numbers because all of the outputs are scalars. However, in practice we usually work with a vector value function. If that's the case, we will often apply the type of derivative that is used when the function has a vector as an input and produces a scalar as an output. So let's assume that the input x is a vector of dimension n. So instead of using a real number, now we're using a vector. Why is this still a scalar? And the output is considered to be a scalar, so it's an element of a real number. In this case, the final computed gradients will be a vector instead of a real number, so they depend on the dimension of the input. This type of derivative is called gradient because they're no longer derivative, and we are accumulating gradients and then creating a vector of gradient derivatives, so it's called a gradient. And it is actually a vector of the same size as the input x. Another familiar term is what is known as a Jacobian matrix. If you have taken a class of matrix theory, you might be familiar with a Jacobian matrix. In order to see how a Jacobian matrix works, we need to use a new example. So let's assume that we have a function y and it's f of x. So x is the original input, and when it goes under the computation node f, it gives us an output y. Then we pass this y inside of another computation g, and it gives us the output L. So this is a chain rule, since it is a function of another function. And let's consider x to be an n-dimensional vector, and y, the output of this function, be m-dimensional vector. So dy with dx is not going to be a scalar, and it's not also going to be a vector, but it's going to be a Jacobian matrix. So if you have a function with n-dimensional input and m-dimensional output, which is y is equal to f of x, the complete gradient is a matrix of the derivative of every output with respect to every input, called the Jacobian matrix. You're not only going to compute derivatives of each element for the vector, you're also computing for y and x. So this is going to result in an n by m Jacobian matrix. And the dimension of the Jacobian matrix is dependent upon the dimension of the input and output. If you have a second function L is equal to g of y that takes m-dimensional inputs, that is the same dimensionality as the output above. So the output from this y has a dimension of m, and L is a function of y, it's g of y. And it returns a scalar output. So the dimension of L will be a 1. It doesn't have dimension because it's a scalar output. You can express its gradients with respect to y as a column vector b, which is really just one column Jacobian. So the partial derivative of L with respect to y is just a 1 by m Jacobian vector. This might seem a little bit complicated, but let's see how this works in detail. So from the previous demonstration, we have L, which is the final output, is g of y, and y is given as f of x. So L is equal to g of y, and since y is equal to f of x, we have g of f of x. We say that x is n-dimensional vector and y is m-dimensional vector, and L is a scalar output. So we have an n-dimensional vector coming in, and the output from this one will be m-dimensional vector, and then the final output will be a scalar output. So when the gradient is being computed, they're not going to be scalar because we have a vector as an input. We know that they're not going to be a vector for the output of f of x because the output is also m-dimensional vector and it's not a scalar. So since the input is a vector and the output is a vector, the gradients computed must be a matrix for dy by dx. So according to the chain rule, if we want to compute the partial derivative of L with respect to x, So from L back to X, by using the chain rule, we have to use the intermediate derivatives. The first one is dy with dx, and it's going to be a matrix. And the second one is dl with dy, which is another intermediate derivative, and it's going to be a vector. This is a vector because y is vector and L is a scalar. If you have the input as a vector and the output as a scalar, then the computed gradients are going to be a vector. Then finally, when you multiply these two, the first one will be a Jacobian matrix, which is an m by n matrix. This is because here we have n rows and m columns, so it's basically n by m. Maybe we can change the positions of these two. And here we have m rows, so it's a 1 by m. So if we take the transpose, it will be m by 1. Then this one will be a 1 by n because we have n as the last element. So basically what PyTorch is doing when you provide a vector as an input and a scalar as an output is basically trying to compute the Jacobian matrix for the first one between y and x, and a Jacobian vector for L and y, and then it multiplies these two to get the final dl with respect to x directly from L to x. So notice up to now that we have been calculating gradients for both inputs x and y. We're using both x and y to compute the gradients. We're using both pathways. But in neural network, gradients are computed and tracked for weights or biases and not for the input x. We don't want to calculate gradients for the input. We don't want to compute dj with respect to x because these derivatives are not going to do anything to the inputs. What we want to do is to compute the gradients with respect to the weights, because the weights are the ones that need to be updated, because the purpose of the gradients is to adjust the parameters or weights. So we need to compute dj with respect to dw in the case of a neural network, and also for bias because it is also a parameter. This will lead us to the question, how could we turn on gradient computation for some nodes and not for others? How could we keep track of the gradient computation for the weights and not for the inputs? In order to see how this works, we're going to use another example. So this example shows the forward and backward propagation for a simple linear regression algorithm. First, we have input nodes are shown as blue to differentiate them from parameter nodes, which are shown in orange, and the computation nodes are shown in yellow. So input nodes, we don't need to calculate the gradient for input nodes. So as you can see here, the pathway is just going directly to the weight. And we can also calculate the gradients with respect to the bias. But in this case, it's just showing the gradient computation when we go from the final output to the parameter. So in case of forward propagation, we're using x and w to compute the next function u. So if the input is 1 and 5, then 1 times 5 will be 5. Then we have one bias, so weight times input plus a bias, which is 5 plus 1 will be 6. Then as we move here, we have another incoming 2. So we're going to take the difference between 6 and 2. 6 minus 4 is equal to 2. This y is not a bias, but it's a target. This might be the prediction from our linear regression model, which is indicated by y hat, because y hat is computed as u plus b, and u is x times w. And here we have y hat minus y, so we subtract 6 minus 2, which is 4, and we're going to assign it to e. And finally, the loss will be a mean squared error, which is the square of y hat minus y, which is e squared, and it's going to be 4 squared 16. Now we have computed the cost for a simple linear regression algorithm. So in order to go back to the weights and to compute the gradients to update the weight matrix, we need to get the intermediary gradients. Since we have a scalar input and a scalar output, we don't need to worry about the Jacobian matrix because they are not vectors. And these gradients will always be a scalar. The first intermediate one will be dl with or dj in this case with respect to dE. And in order to compute that, we're going to do dj with dE. Once we compute dj with dE here, this one is dj with dj, and by multiplying them we get the next one. And here we multiply this one with dE with dy, is the intermediate between the paths from e to y hat. So by multiplying dj with over dE by dE with dy hat, we can get dj by dy hat. We can cancel the terms dE here. And finally, we move backwards and then compute dj with dw. So by substituting the values here, we can get 8 for each one of them. So we're computing first dj with dE. Then second, we're computing dj with dy hat, from dj to dy hat. And finally, we're computing dj with dw, from dj to dw. And you can go through how each of them are computed, but basically what it's doing is using and applying the chain rule and to go back to the initial weights. And notice here that we are differentiating between x and w. And PyTorch has a specific method in which you can assign gradient tracking for some nodes and not for others. This leads us to a new package in PyTorch known as Autograd. To calculate gradients and optimize our parameters, we will use an automatic differentiation module in PyTorch called Autograd. The Autograd system is designed particularly for the purpose of gradient calculations. Automatic differentiation can be performed in two different ways. These are forward and reverse mode. The forward mode that we calculate the gradients along with the result of the function. So in a forward mode, we'll be calculating the gradients when we are in forward propagation mode. So with the result of the function, we are computing the gradients. While reverse mode requires us to evaluate the function first and then calculate the gradients starting from the output. So in this case, in PyTorch, what it's doing is first evaluating the forward propagation, the forward mode, and once you get the final output, then you use reverse mode to compute the gradients. But in forward mode, it's just basically computing the gradients when we are computing the outputs for each function, and it doesn't wait until we reach the last function. This is a very basic concept, but you must understand how PyTorch differs from other deep learning frameworks because it computes gradients in reverse mode, which means you have to wait until you compute the output from the final function, and then by using reverse mode you can compute the gradients. You cannot compute the gradients side by side as you move forward along the path. While both modes have their pros and cons, the reverse mode is the de facto choice since the number of outputs is smaller than the number of inputs, which allows a much more efficient computation. Most of the time when you deal with neural networks, the number of or the dimension of the output is always going to be less than the dimension of the input for most cases. In some natural language processing experiments, you might find that the output might be greater than the input, but even in that case, the reverse mode also works and still efficient when compared to the forward mode. So we have mentioned that we can track gradients for some variables and we are not required to compute the gradients for other variables. So how do we turn Autograd off and on using PyTorch? Previously we mentioned that gradients are computed and tracked for weights or biases and not for the input x. So we need to keep track of gradients of some variables such as the weights and biases and not for the others such as the input x. How do we do this? To compute the gradients, a tensor must have its parameter requires grad equals to true. The gradients are same as the partial derivatives. So let's say the first input is a and it's just once a tensor, a two-dimensional tensor, which is a 2x3 tensor, and all elements are ones. And if you provide the argument requires grad is equal to true, PyTorch is going to build a computation graph starting from this point, and a is going to be your first input. Since you turn the gradient tracking for this tensor, that means gradient tracking or gradients will be computed for this tensor. First, we must import the torch library in order for this code to work. Then we can create a PyTorch tensor by setting requires grad is equal to true. When we do this, PyTorch will keep track of gradients for this tensor. In the figure, we can see that b1, which is the next function, is a multiplication because we are multiplying a by 2. And it's a multiplication function, and whenever you turn on the requires grad attribute to true, anything that performs any operation on this tensor is going to be considered automatically as part of the computational graph. And since it is a multiplication operation, PyTorch under the hood will automatically assign the grad fn attribute, which is mul backward, which stands for multiplication backward, which is what we expect since it was derived from a tensor that has the Autograd attribute turned on. When we turn off Autograd explicitly with requires grad is equal to false, you can see this here, computation history is no longer tracked, as we see when we compute B2. Next, we turned off the requires grad attribute, and when we first create the tensor, we can provide the requires grad parameter as a parameter to the tensor. But once it is created, if you want to turn it off, then you can use the attribute requires grad of the tensor itself and assign it a value of false. Then when we multiply a by 2 and assign it to b2 and print out the output, we can see that the final output doesn't have the grad function inside. So b1 has a grad function attribute assigned to it when we output b1 here, because the requires grad attribute has been turned to true, and this computation will be considered part of the computational graph. But when we turn it off again, starting from this point, any operation that we perform on this tensor is not going to keep track of the gradients. That's why we don't see the grad function attribute for the second one. To compute the gradients, a tensor must have its parameter requires grad set to true. The gradients are same as the partial derivatives that we have been computing in the previous slides. Depending on the function used, PyTorch will assign the grad function. In this case, it's mul backward, since b1 is equals to 2 times a. This grad function attribute is just the nodes, the computational nodes, the yellow ones that we have been talking about in the previous slide. So if we use multiplication, then PyTorch would automatically know that it's a computation node and give it a name known as mul. If it is an addition, then it's going to say add, a difference, then sub, and so on, depending on what kind of operation you use on the computation node. So in this case, since we are multiplying in order to get the second computation node, PyTorch is always going to assign a grad function attribute by itself and give it the name mul backward. How about turning Autograd off temporarily? If you only need Autograd turned off temporarily, a better way is to use the torch.noGrad attribute. Remember when we set the requires grad attribute to false here, that we no longer have access to the computational graph built here. So starting from this point, A is not going to track its gradients. But if we just want to temporarily stop tracking gradients on certain part of the code and then continue for the rest of the code, then we can do this by using torch.noGrad method. So we can see this by using this example. We're defining two tensors, and both of them are a 2 by 3 rank 2 tensors, and all elements are ones. Then we multiply the first one by 2, and we have discussed in the previous video about broadcasting. It's going to broadcast the second tensor and multiply and transform this scalar into a shape of 2 by 3, and then multiply all the ones by 2. Then you have a tensor of 2's. Then this is going to do the same and multiply by 3. Here, notice that we have provided the parameter requires grad is equal to true. And when we compute C1 is equals to A plus B, this intermediate computation node is the sum of two tensors in which the requires grad attribute has been turned on. So when we print the value of c, it's going to add a tensor of 2's to a tensor of 3's. Since the dimension is 2 by 3, it's going to be 5. Then the grad function here for the computation node is going to be add backward, which is automatically assigned by PyTorch. Notice here that we are using with torch.nograd, and you can put any section of a code in which you don't want to compute any gradient on, or in which you want to turn off gradient tracking under here. And here we're computing C2, and we're basically doing the same operation A plus B. But when we output C2, one thing we notice is that the grad function attribute has not been assigned to this output, because we say that we want to turn off Autograd temporarily. So we're not tracking any gradients or computing any gradients when using C2. But moving on, when you use A and B again and multiply them to compute C3, since this section of the code is not under the torch.nograd, it's going to be part of the computational graph, and it's going to be assigned the grad function attribute again, which is mul backward, which is a product of A and B. Notice here, when we assign the requires grad attribute to false, any part of the code that is coming after this point is not going to be part of the computation graph because we have turned the requires grad to false. But this allows us to temporarily remove gradient tracking and then proceed using the computation node to be part of the computational graph. Finally, you may have a tensor that requires gradient tracking, but you want a copy that does not. For this, we have a tensor object's detach method. It creates a copy of the tensor that is detached from the computation history. So what it's basically saying is that, let's say we have a new tensor, which is rand stands for random numbers, and we need 5 elements, and we're turning the requires grad attribute to true, and y is equals to x dot detach. And when we print out x and y, we see that the requires grad attribute has been set to true for the first one, which is x, and the requires grad attribute has been turned off again for y. So the detach method is another method to turn off the gradient tracking temporarily by using the method of the tensor itself. If you have provided requires grad to true to that tensor, if we detach and assign it to another variable, that means we're detaching, or we're saying that we don't want to keep tracking the gradients. So the requires grad attribute will be gone. Finally, after we have covered the point of the requires grad attribute, we need to talk about the backward function and the grad attribute. Remember that we have said PyTorch Autograd computation can be done in forward or reverse mode. So far, PyTorch is keeping track of the computational graph but not computing gradients. Since we are moving forward and it's forward propagation, we have mentioned that in reverse mode we have to wait until we reach the final function before we start computing the gradients. So when we move forward, it's just keeping track of the computational graph, but it's not computing the gradients yet. So if we want to compute the gradients, the most efficient way to compute the gradients is in reverse mode, and we need to call the backward function on the final output. So we need to wait until we reach the final output, and then once we get the output from the final computational node, then we call the backward method on that final output. Under the hood, PyTorch is going to compute the gradients using the backward function, and by using the .grad attribute, this is a grad attribute that we mention on the title, enables us to access the gradients computed for the original tensor in which we turn on the requires grad attribute. So in this case, the grad attribute can be called on X, since it's the one that's keeping track of the gradients, and assign it to the variable dx, and when we output we can see that x.grad, the computed gradient value, will be 4. To get the gradients, we can use the grad attribute of the tensor, where the requires grad attribute is set to true, and we can use the following example to explain the whole process. But before we move on to the multi-dimensional output, this example gives us some explanation about for a single input or a scalar input. Notice x is just a tensor and it has one element 2, and the requires grad attribute is turned to true. When we print x, we get a tensor 2, and notice now we have the requires grad is equal to true even in the output. Y will be a computational node because we are performing some kind of operation on the tensor x. We are squaring it and adding 1, then 2 square will be 4, 4 plus 1 will be 5. Since it is a computational node, for any computational node, it's going to be assigned a grad function attribute by PyTorch, and since it is an adding operation, it's going to give it the name add backward. Finally, we have decided that this computation node is our final computation node, and when we call the backward method on the final output, then we see that the gradients are going to be computed. This value 4 will not be computed if we don't call the backward method first. Then finally, by using the grad attribute, we can access the gradients that have been computed for dy by dx. But what if the input is not a scalar but a multi-dimensional output? What if the output wasn't a number but a vector? For a multidimensional output, Autograd expects us to provide gradients for the outputs that it can multiply into the Jacobian. Notice previously that we have mentioned if you have an input or output which is multidimensional, then you need to provide an argument for the backward method, otherwise PyTorch will give you an error. If we tried to call the backward method, we would get a runtime error and a message that gradients can only be implicitly computed for scalar outputs. You don't need to provide an argument for the backward method if the output is a scalar. You just multiply and then you get a single output. But if you get a vector as an output, then you have to provide a vector as an argument for the backward method that is going to be multiplied with the Jacobian that is computed by PyTorch. So let's see this example. First, we are using rand_n to generate random numbers which contains 3 elements. Then we're going to multiply them by 2 since we turn on the requires grad attribute. Y is going to have a grad function assigned to it by PyTorch. Then we're going to just multiply y by 2 again and assign it to y until y.data.norm is less than 1000. You don't need to worry about this operation. But when we finally print out y, we can see that the output is not a scalar but a vector. So here you cannot call the dot backward method and not provide an argument here, because under the hood we have seen from the previous slide that a Jacobian matrix must be multiplied by a vector input in order to compute the another vector. So we can go to that slide and let's revise again. Here the Jacobian matrix is the one that is computed by PyTorch, and here you must provide this vector by yourself to the as an argument for the backward method, and then finally it gives you the final computed gradients for dl by dx. Since it is a chain rule and we used two functions to get from the input to the output, it's basically a product of the intermediate gradients to get the final gradient vector. So just be aware of this situation, and once you understand why we provided this vector as an input, then you can use the grad attribute to access the final vector. Notice that the gradient that is computed finally is also of the dimension 3. Okay, that was a lot of concept, and I want to congratulate you for making it this far. And next we will see the implementation of gradients by using PyTorch.
Audio Jungle.